Thank you very much for having me here today. I'm Alex Blair from the UK Atomic Energy Authority, talking a bit about our work in getting an open source application to enable setup of MFEM problems and assemble them in the LIS framework. And our application is Platypus for naming reasons that will come evident in a minute. So as a quick show of hands very quickly, how many people here in the room have actually used Moose before? With practically one? Most are. Okay, cool. There'll be instructions there anyway, so hands up. So I'm just going to go a bit kick off as to why we UKAEA care about any of this in the first place, what motivation is, and our involvement with Moose at UKAEA. Before introducing Platypus explicitly, going through a few examples and like a Fusion example in a bit more detail to show what it looks like from a user perspective, before going into the future work and wrapping up with some learning in the rest. So why we care is fundamentally we know in the Fusion community, which we at UKAEA, we're trying to reach the goal of commercial fusion. We know there's not going to be sufficient experimental data by the kind of timescale our next-gen fusion reactors are going to come online for to fully qualify components. So there's this enormous need to provide our engineers with the kind of scalable multiphysics simulation tools that they have to use to do the substantive assessment and de-risking of the components that are required for these reactor designs, and do so in silico. And the commercial shelf tools simply can't reach the kind of complexities and degree freedom we need to do this. And we've got a whole host of different bits of physics, spanning time frequency domains that we care about here. There's mechanical problems with contact, which was so most of the Serac talk yesterday. We've got to worry about electromagnetics, we've got to worry about neutronics, we've got to worry about tritium transport, we've got to worry about fluid flows. It's everything everywhere for some of these components, and it's a tricky challenge. So we need to provide tools that our engineers can use. And in our group specifically, UKAEA is a broad church, but in the group I'm part of, the Advanced Engineering Simulation Group, I work under Andy Davis, where we are in this particular group currently around 20 people or so, currently growing, where our reason to live, as it were, is to provide the engineers with the tools they can use to run these actionable simulations on realistic complex geometries and the fusion relevant physics problems to help answer the key engineering questions to work out whether or not they're appropriate for them use cases. And we work with a whole range of tools, things like OpenFlow, NeckOS, OpenMC, but the kind of base platform that we're using as kind of the underlying framework to bring everyone together is Moose, for a few reasons. But before we go into any of those, it's probably worth describing a little bit about what Moose is. So Moose is an open source parallel finite element framework from Idaho National Labs, collaborating with in this. It's got a large user community, as we heard yesterday, with the number of star race between Moose and MFEM, that has a whole host of a wide range of current existing well-validated physics modules that are available out of the box. And this was one of the reasons UKAEA we were drawn to this a few years ago when we kind of using this as a base platform was chosen, because it meant we could get our engineers over to using large-scale tools that can be used to HPC workflows for their problems pretty much out of the gate. And it's got a simple user interface for problem definition, a modular way of adding new kernels, new integrators to a specific problem from a user endpoint. Again, the audience here is the end user, being engineers adding extra terms to their problem to solve and building that problem up for a range of potential separate validation cases. And demonstrating scalability on some of those existing modules for up to CPU calls. But it has its limitations, and they tend to come back to a lot of them come back to the underlying finite element library it uses, libMesh, that I personally hit a few of these roadblocks myself when I was trying to get some capabilities in for electromagnetic, solving electromagnetic problems. So specifically things like it has relatively limited support of vector element type, which correlative conforming modal electromagnetic MAR, and there's, for instance, lack of support for Dirichlet boundary conditions on those at the moment. It doesn't, all the preconditions are often used to solve the kind of problems that I was trying to tackle, like HyperMS, weren't able to pass in the fine grid information that set up that are required to make them perform. Although there's some work going on at the moment on libMesh to help address that. And compared to something like MFEM, obviously no GPU support. And there's a few other things as well regarding restrictions on the order of the IP types that can be used in libMesh due to a relatively weak separation between the concept of a mesh element and a finite element. But we also, so I played around getting some MOOS applications, some MFEM applications to be able to solve our EM things and wrapping them with MOOS following a very similar procedure to a whole host of other widely used MOOS-based applications like Cardinal, one of the MOOS-based applications over Argonne. And had some success with that in building some of our support for, some of the building things for induction heating experiments, UKAEA, did it this way. But it doesn't solve the fundamental problem here of being able to set up and build and solve fundamental problems directly using MFEM. And as a result, things like going on outskirts of physics. So here comes Platypus, and our current effort is probably about 6 months old by now, to help address this problem and this work. And the whole goal is to try and enable the setup, assembly, and solution problems from the MOOS like input stack in the MOOS framework, but using MFEM under the hood instead of libMesh. It's open source. You can go to the link here if you would like to have a play. We've got a host of things that are built every week to help new users get to grips with things. We're planning our first release soon. Just going through a documentation review for that. It can currently handle on CPU or GPU single variable square systems from recent stack for linear problems at least at the moment. This is planned to go through. We've got at least 4 years plan at the moment to work on this. So this is the beginning of a road, and we're hoping to build features in to get this up to at least that we see in the libMesh based dimensions. So what does it actually look like for a user? This is on the right hand side here is a Platypus input file that we started the application to solve the classic diffusion problem with educational involved these vector in this case. This is effectively an example. It's probably the first example if you do end up picking up MOOS at any point directly. Probably the first example that they show up in their tutorials. But rather than solving this using libMesh under the hood, we're solving it using all the ways that all this is controlled fundamentally is through a custom problem type that the user specifies in their input file. We'll do some input problem rather than anything else that lives in this moment, and that is that means that the builder class that is used to use under the hood to build and enable the library objects is aware that it wants to do that with MFEM rather than libMesh. And so this is the kind of crucial builder class that starts with accumulating to structured objects rather than libMesh. You'll see in the next few slides, I've very deliberately put a comparison to what this would look like in regular MOOS file. You might find very interesting examples. So you can hopefully see that we're trying to keep things as familiar as possible for existing MOOS users, because as we mentioned at the start, that large existing community is a really big draw that we really like to be able to provide a tool, given the option of using that buttons, libMesh, and making sure that the user interface is similar as possible to what they would be used to. Step in. So the problem is the key declaration to tell the users that they'll tell the application rather that the user wants to build using MFEM rather than we set the mesh definition. It sets up MFEM par mesh under the hood. This thanks to the new updates to get to read qubit and the various extra file support. We are able now to read in most of the all of the native loose files. There are existing examples that most of those are extra format, so it's been extremely useful for this purpose. And declaration of finite element variable. It's just effectively a grid function with its associated finite element states. As I said, Moose doesn't really separate the concepts particularly clearly between the mesh element and the finite element, and so they just have a single variable block here with declaring the order of boundary, whereas we have the capability of really using FE spaces with more grid functions as unlike evil and MFEM. But we can actually, if the user isn't familiar and just wants to copy these over, we do support similar syntax and create a sort of appropriate finite element space for a loose variable node that happens. If the user isn't explicit about how that spins up. In terms of setting up the actual problem being solved, we have an equation system object under the hood that we accumulate bilinear form integrators and linear form integrators onto linear form and linear form of the problem. These are in a similar way to the domain integrators are handled in the kernels block, which you quickly see almost identical through existing loose, and these kernels are really just integrators with some spatial extent. So a set of blocks of domain attributes which you wish to apply the kernel, and the pipe which defines which domain integrator for coefficients and the piecewise coefficients that represent material properties. We have this materials block by analogy with Moose, which they can be functions of where they could be functions in constants in this case. And this is how we track to make sure that we build up that piecewise coefficient in an appropriate way consistent with how the existing Moose would things. And as a result, we have this is declaring the addition of the kernel and then it's very up to people. For boundary conditions, it's fairly similar for integrated boundary conditions. For Dirichlet conditions, for essential boundary conditions, we have vector we. Here we're just finding out, say, working instance on the mug here. We can explicitly tell Moose to construct coefficients without going through material interface that we want at the moment. We may be unifying this to look a little bit closer to Moose and have Moose functions directly specified in that problem, set up an MFEM function coefficient to help with some of this. But I think you keep things very, very similar. So we can handle integrated potential boundary conditions in this. And for solvers, we have some solver abbreviation blocks, and which are handled in the executioner, which is a Moose concept for the object that actually handles the solver itself. The executioner is a low block. This critically, we're able to where we have the ability to set the device to be not just the CPU, but CUDA and other assembly levels as appropriate. Whereas we'll see in Platypus, that's not an option. Our outputs, we can also output to the current view data collections and visit data collections using the Nuke's output system. Very similar to the output is just some data collection, but the ability to execute on different at the end of time steps or the end of the whole simulation, or some interval thereof every 70 time steps, if you so wish, is all handled by the existing Moose output system, which gives you a bit of flexibility inherited from Moose study. And so crucially, we can do things already in this in native Moose. We're finding very similar performance at the moment to this is an example just using full assembly that we didn't need on some 100s. And we've compared to a native MFEM, so example 1, comparing to Platypus, and we're not seeing significant differences. It's a relatively small problem, but we're not currently seeing much of a difference between the two so far. It's not the only addition to what we can do in native in Platypus at the moment, as I'm partially committed to native Moose. We can also, I mentioned earlier that native Moose can't handle the kind of passing in by problem information. Well, it's hyper-AMS, nor connectivity well handled the zero-trade additions on vector P56 directory. So we show here an example reproducing MFEM example 3. Other code pretty much setting up the same problem as you're familiar with from the MFEM examples set, but done from Moose rather than. And this is particularly useful in designs. And it's not always restricted to steady state problems. We've also got a support for transient problems. I believe we don't yet have the assembly on GPU for this, but it's up in a draft PR, I think, at the moment. It's almost ready to go. Whereas this is showing an example on a simple transient heat conduction problem that separate one again, similar to how you would expect from writing a Moose. Also show a little example here of how we can handle passing in use functions to define MFEM function coefficients as a function of space and time or those services. So we have some level of interoperability with the existing Moose function system. So it's for that. Again, useful when wanting to pull over. Now looking to the future, we've got the next thing on the docket is mesh updates and deformed problems and displaced problems. We again have got currently up in a PR this for a steady state case with extended transient motion problems. This is just again a version of appendix example 2, but from Platypus set up in similar way you would expect from Moose. Passing in the variable displacement, passing it in to the mesh, that variable is suitable to displacement, and again setting out the rest of it integrators and sheets appropriate. And this is step 1 in our plan for making sure we're adding in the mesh updates where appropriate as needed for transient problems and AMR. Making sure we can communicate to the mesh when we want update to crowd. One big one we're adding for interoperability purposes is transfers. So Moose, if anyone who has played with it, has this idea of a multi-app framework where multiple input files can perform parts of a larger simulation and transfer data between these sub-apps. Now, what we would like to do is have transfers between MFEM sub-apps to MFEM sub-apps and MFEM sub-apps to and from libMesh-based sub-apps. We're pretty confident we can do this for simple E-types because of our previous work on the EM work we showed earlier. So we had transfers working between we had sync solutions to be able to map between basically the permutation arrays between libMesh variables and MFEM bridge functions existing on lowest order and first and second order Lagrange and thermal decomposing polynomials for hexes, tets, wedges, possibly some for knowing at least where the node ordering is in the meshes for pyramids. So we're confident we know what those orderings are and how we can transfer those data, but we've yet to bring across to the de facto sort of needs out together. Why this is particularly interesting is this should now allow us to support use cases where one sub-app could be running an existing loose framework, or multiple sub-apps could be running existing loose framework solves, exchanging data and copying data from MFEM grid function onto a variable that's used as an auxiliary source or something that can be used in the vision and vice versa. So yeah, work ongoing on this, and we've started work on this as well. And where the kind of direction of travel is and what we really want to tackle are the kind of large nonlinear mixed problems that of the type that are currently being solved by the organization in this is a picture of a commissioning sample, a test for CHIMERA simulated by Andy Davis. That's really part of our facility for to help validate our codes. Coming up with CHIMERA, will be helping to test components under high under EM loads, under transient magnetic fields, under high heat conditions, fluid flow in the pipes, and everything all at once, outside of a radiation field. And we need to be able to get to the stage where we can solve this using MFEM-based workflow. So we're working at the moment on extending what is currently all linear to supporting use of non-linear form and in bulk height to be said. As Moose uses the existing work with this, extensively uses differentiation kernels in Moose, and so particularly paying attention to the work currently with enzyme, DCAM, because it's very much something that could accelerate. It solves this way. Very much of interest for enabling this. So to kind of wrap up, we really do need to be able to provide some simulation tools at scale for our engineers to really tackle the kind of large scale problems and economies that we're giving them in engineering challenges, because we just won't have data available. And so Platypus is to help us do that using MFEM as the underlying backend to solve these problems on CPU or GPU, speed and loose. And we've already demonstrate some of that today. And we've got support at the moment for solving single variable steady or transient linear problems, with the first formal release coming soon once documentation is reviewed and approved. So thank you very much. Very happy to take any questions.